In this video, we're going to return to circuits, and we're going to explore a new circuit element that we've never seen before, the inductor. To explain what an inductor does, we will first examine the behavior of two circuits side by side. As we can see, both circuits contain solenoids. The circuit on the left has an AC generator, but the circuit at right does not have a generator or a battery. It has no power source at all. Now, let's expand on what we know about the circuit on the left. When a current passes through a solenoid, it will produce a magnetic field, because all currents generate magnetic fields. You might remember that the equation for a magnetic field of a solenoid is given by this variant of Ampere's law, μ0 Ni, where N is the number of turns per meter. But from the last video, we know that an AC generator produces a variable voltage and current. That is, both the voltage and the current change over time. Since the current is varying with time, that means the generated magnetic field will vary with time as well. The field lines of the magnetic field generated by the left circuit pass through the area enclosed by the solenoid in the right circuit. That means the solenoid at right is feeling a magnetic flux caused by the solenoid at left. And since the magnetic field from the solenoid at left is changing, that means the magnetic flux passing through the solenoid at right is also changing. So, the solenoid at right is feeling a changing magnetic flux. And according to Faraday lens from a few videos ago, a wire that feels a changing magnetic flux will respond by creating a counterfield, which in turn means it will develop its own voltage and current. So, let's briefly review the steps of this process. The left circuit contains a current, so it creates a magnetic field. As the current in the left circuit changes, the generated magnetic field also changes. The right solenoid feels a changing magnetic flux. The right circuit opposes that changing magnetic flux by creating a counterfield. And to do this, it must develop a voltage and a current. We can summarize this process with this equation. The voltage that develops in the second circuit is equal to -m times the rate of change of the current in the first circuit. I won't go through the whole derivation, but basically this says that a changing current in the left circuit has induced a voltage in the right circuit. In this equation, M is a constant. It is called the mutual inductance of the two circuits, and it's measured in a unit called henries. Mutual inductance is usually easier to measure than it is to calculate, because the relative locations and sizes of the two solenoids can make the calculation quite complex. Now, we are going to take the process of mutual inductance one step further. Suppose, instead of having two circuits, we have only the left circuit with the AC generator and the solenoid. The generator creates an alternating current, and the solenoid produces a changing magnetic field, just as before. But now look what happens. The solenoid is not going to feel a changing magnetic flux from some external magnet or from another solenoid, but it will feel its own changing magnetic flux. Now, Faraday lens says that any wire that feels a changing magnetic flux must create a counterfield to oppose the change. So this solenoid here will create a counterfield that opposes its own change in magnetic field. So now the steps are as follows. The AC generator causes the current in the circuit to change. As the current in the circuit increases, the solenoid's generated magnetic field also increases. The solenoid feels its own changing magnetic flux. The solenoid opposes that changing flux by creating a counterfield. To do this, it must develop a counter voltage that opposes the original change in current. In short, the solenoid uses a change in current to create a counterfield that prevents further changes in the current. We can summarize this process using this equation. In this equation, L is a constant called the self-inductance of the solenoid. It measures the effectiveness of the solenoid at smoothing out changes in currents. Once again, the solenoid uses a change in current to prevent further changes in current. Self-inductance is considerably easier to calculate than mutual inductance. I won't go through the whole derivation. The punchline is it equals mu0 times the number of turns in the solenoid squared times the area divided by the length. An inductor is a circuit device that uses the self-inductance of a solenoid to smooth out changes in current. Consider this ordinary DC circuit. It has a battery, so the source voltage is constant, unlike the AC generator we were using before. When we first started talking about circuits, we saw that the current was given by Ohm's law, V equals IR. Rearrange that and you get the current, I equals V over R. Battery voltage over resistance. That's important. Current equals V over R. But an inductor tries to prevent changes in current. So if an inductor is introduced to the circuit, what started as an instantaneous jump in the current turns into a gentle rise that looks like this. So the current in the circuit changes over time. The current at any time is given by this equation. I equals the maximum current, V over R, times 1 minus e to the negative r over L times time. E is a mathematical constant like pi. It has a value of 2.718. When we graph this equation, we get a shape like this. The current gradually approaches its maximum value of V over R. The greater the inductance, the longer it takes to reach that value. But the greater the resistance, the less time it takes. But if you look at this equation closely, you notice something interesting. The current will get closer and closer to V over R over time, but it never actually reaches V over R. So it doesn't make sense to talk about how quickly or how slowly an inductor circuit reaches V over R because it never does. Instead, we talk about how long it takes for the inductor to reach 63.2% of V over R. This seemingly random value is actually a very logical choice because 63.2% is e to the power of -1, so it's closely tied to this equation. The time that's required for the circuit to reach 63.2% of V over R is called the time constant, and it is symbolized with the Greek letter tav. It so happens that tav equals L over R, inductance over resistance. That quotient tells you how long it takes to reach 63.2% of V over R. All of what we've seen so far corresponds to the circuit as it is turned on, but a similar logic holds as the circuit is turned off. Instead of immediately falling to zero, the current gently decreases, as shown in this graph. The equation is similar to the equation for the circuit being turned on, but the 1 minus is missing in front of the e term. The time constant is exactly the same as before, L over R. Now, let's try an example. Suppose you have a circuit that contains a 5-volt battery, a 10 ohm resistor, and a 2 Henry inductor. How long does it take for the circuit to reach 90% of its maximum current? We're looking for a time. Let's substitute all the information we know. A current of 90% its maximum value would be 0.9 V over R. We substitute that in for Y. When we do, we end up with V over R on both sides. We eliminate those variables. Moving some terms around, we get e to the power of negative 5t equals 0.1. The next step is to get rid of the e. To do this, we take the natural logarithm, ln, of both sides. This gives us negative 5t equals the natural logarithm of 0.1, which is negative 2.303. Finally, divide both sides by negative 5 to get the time, 0.46 seconds. This is how long it takes for this inductor circuit, this RL circuit, to reach 90% of V over R. If the equation for an inductor looks familiar, that's because we saw similar equations when we were talking about capacitors. In fact, capacitors and inductors frequently behave in exactly opposite ways. When a circuit is turned on, an inductor causes currents to slowly rise to their maximum. By contrast, a capacitor causes currents to start at their maximum and gradually decay to zero as it gets more charged. Something similar happens when the circuit is turned off. An inductor keeps the current flowing in the same direction until the current decays. Whereas if you took the battery out of an RC circuit with the charged capacitor and reconnected the wires, the current would move in the opposite direction until it decays. This video introduced the idea of self-induction and showed how an inductor works in a DC circuit. In the next video, we will apply it to an AC circuit as well.